And the name of the game is really, can you tell the difference between these two boxes? So you're getting one of these boxes at random. You don't know which you got. And you are allowed to ask several queries to this box. And you need to tell which box you got. And the quantum algorithm is able to do it very efficiently. It would run in time which is logarithmic in the length of this truth table. Whereas we'll show that classical algorithms, and in fact algorithms in the entire polynomial hierarchy, cannot tell the difference. And this corresponds, and we sort of talked about it in length in the last talk, this corresponds to showing that AC0 circuit cannot tell the difference between these two black boxes, and sort of I will keep with the AC0 notation for this talk. Okay, so I want to say what will be our main statement. So first, a definition. So we say that an algorithm or a function f has advantage alpha distinguishing between these two black boxes when alpha measures the probability that f accepts an input from this black box minus the probability that it accepts an input from this black box. Okay, and we think of winning this game meaning is sort of equivalent to having alpha big, right? So if we sort of here accept with high probability and here accept with low probabilities, then the advantage is big. On the other hand, if we cannot tell the difference between the two black boxes, then these two probabilities will be roughly the same, and then alpha will be very, very small. Okay. So the main result is that we present a distribution, the correlation distribution, over strings of length capital N, and you should think of this as really exponential in little n. Okay, so maybe I would write that. So you should always think of capital N as exponential in little n. And we show two statements about this distribution. On one hand, super fast quantum algorithms that work in logarithmic in capital N time can tell the difference between these two distributions, and their advantage would be not so small. It would be roughly 1 over log n. Okay. On the other hand, we will show that any AC0 circuit can distinguish between these two distributions with advantage at most 1 over square root n. Okay, so the advantage of an AC0 circuit is a lot smaller than the advantage that the quantum log time algorithm is able to achieve. AC0, I will show you very explicitly what I mean, but just think of it as just some kind of class of circuits that you will see in the next few slides. Okay, so I don't want to go forward and backwards all the time. Okay. So that will be our goal, and based on this result, I claim that we get the oracle separation. So how do we get the oracle separation? So this is due to many questions that I got in between the first and second lecture. So the idea is to construct the oracle and the language sort of together. So the language would be just a unary language. Okay, so I want to define how the oracle would behave on strings of length n. And we recall that we can just think of it as a truth table of length capital N denoted by, so I'm just denoting how the oracle behaves on strings of length little n by this 8 subscript n. Okay. So I'm going to construct a unary language, and I just need to say which strings of, which unary strings are in the language and which unary strings are not in the language. Okay, so for each input length, I need to make a decision. Do I include these strings of length n in the language or not? So how I'm going to make this decision? I'm going to make it at random. So for each input length, with probability 1/2, I'm going to first, okay, so I make, with probability 1/2, I'm having, like, let's say I'm doing a coin flip and I'm getting heads. If I'm getting heads, then I draw this black box, I draw this AN according to the uniform distribution, and I add the string 1n to the language. And if I got tails, then I draw this truth table restricted to, to inputs of length n according to the distribution D. Okay, so I have this distribution for every input length. And then I don't add 1 to the n to the language. Now, okay, so this is the construction. So we constructed both the oracle and the language. Why can a quantum algorithm decide this language? You get 1 to the n, and you need to decide is it in the language or not. Recall you have access to the oracle. So you can just run your distinguisher and check whether this oracle was sampled according to the uniform distribution or the distribution D. If you got that, you have with high confidence, you figured out that the oracle was sampled according to the uniform distribution, then you can conclude that indeed 1 to the n is in L. On the other hand, if you concluded that the oracle was sampled according to the distribution D, then you would just reject. Okay, so this is everything here holds with high probability, but you can show that for most choices here, there exists a BQP algorithm. On the other hand, what would happen to the PH machine? So the PH machine is sort of, based on the oracle, it cannot really tell the difference. It cannot really tell whether the oracle was sampled according to the uniform distribution or the distribution D. Therefore, it will, whatever choice it will make to accept or reject, it would succeed with roughly probability 1/2, because it needs to sort of guess this coin, and it's hard to guess the coin based on the information that the PH machine got. So for each input length, the PH machine would make a mistake with probability close to 1/2. Therefore, it will make a mistake eventually on one input length. So that's the connection. But from now on, I want you to forget about oracles and just focus on this task. So I just want you to think of, you have two black boxes and you want to distinguish between them. Okay. So the plan for today. So I already defined D, but probably you already forgot. So I'm going to redefine it again. And then I'm going to show quantum algorithm that distinguishes between the D and the uniform distribution. And finally, I will show that no AC0 circuit can tell the difference. Okay. So the distribution D is based on the suggestion of Scott Aronson with some modifications. So the idea is we want a distribution over strings of length capital N. So we want a discrete distribution, but we'll start with a Gaussian distribution over R capital N, from which we'll deduce a discrete distribution. The Gaussian distribution we look at as following. So we are picking x1 up to xn over 2 IID Gaussians with mean 0 and variance sigma squared. And then we take this vector of x's, and we multiply it with the matrix H, and we get a new vector of y's. There are also Gaussian random variables, and in fact, if you look only on the y part, they're also IID with mean 0 and variance sigma squared, but there are obviously correlations between the x part and the y part. The y is determined by x.
What is H?
H is the Hadamard matrix. Right. So, and it's important for the rest of the talk to remember that the entries of the Hadamard matrix are small. Okay? That each entry is small on its own, which would mean, at least here, that the correlation, let's say, between x1 and y1 is small. Okay, so locally, this is sort of almost like like in the independent case, where this entire thing was independent, and therefore an algorithm that only looks locally cannot tell that this is not the uniform distribution. So that's more or less the intuition. And I'm picking sigma squared to be roughly 1 over log n, and the reason that I'm doing it is that I want all the coordinates to be within the interval -1, 1 with high probability. Okay, so I want that whenever I'm sampling this vector, I get that all the numbers are sort of bounded between -1 and 1 with high probability, and that's why I chose this variance. Okay. So how do we make it discrete? So this gives me a distribution over vectors in Rn. I want to make it a distribution over +(-1) to the n. So I'm going to draw first the vector z according to the Gaussian distribution. If one of the coordinates goes outside -1, 1, then all hell breaks loose, and I don't really know what to do, so I'm just going to abort or maybe just output a fixed string. Okay, but you shouldn't worry about this case too much because with high probability, we will not end up here. Okay, so now let's just assume that all the coordinates are between -1 and 1. I'm going to think of them as biases of coins. So I have n numbers. I think of them as biases of coins, and I'm going to draw random coins with these biases. So if the first number is, let's say, 0, then I flip an unbiased coin whose expectation is 0, right? So it's 1 with probability half and -1 with probability half. Its expectation is 0. If the seventh coordinate is 0.9, then I flip a biased coin, which is more likely to give me a 1 than a -1. And I'm doing it independently across coordinates. And I want that the expectation of zi prime would be zi, and zi prime is a ±1 random variable. So this is just, sort of randomized rounding. I'm taking these vectors over the reals, and I get a distribution over ±1 to the n. Okay, so that's the formal definition. I just want to mention that the original definition was similar up to this point, but then to go from the Gaussian to the discrete setting, you just take signs. I don't know how to analyze that. So I know how to analyze it with randomized rounding. Okay, so why is there a quantum algorithm that can tell the difference between this distribution D and the uniform distribution? So actually this distribution sort of came up with the quantum algorithm together. So it's not super surprising that there exists such an algorithm. So this was suggested by Scott Aronson. Yeah.
Can you go back one slide? So you round all of the coordinates, like all of the n coordinates.
Mm-hmm.
Basically independently.
Right.
Okay.
Yeah.
Just repeat the question.
So the question was, so this was more a clarification saying that you look at every coordinate and independently you draw this random variable z prime I with expectation equals zi, and this is independent across coordinates. Okay. So Aronson, and this was simplified by Aronson and Ambanis, they gave a very fast quantum algorithm, let's call it Q, such that the acceptance probability of the algorithm on a given input x, y. So think of this input, I think of x and y as strings of length n over 2. This probability equals exactly 1/2 plus the inner product of hx with y divided by n. And I also want to remind you that we call this thing hfx with y, we call this the correlation of x and y. And really, our task is to distinguish between strings that are uniform and strings that have high correlation, that have high inner product under this, after we apply Hadamard on the first part. Okay, so we're going to show the algorithm in the next slide, but let's just assume that this statement is correct. So notice that this probability is over sort of like the randomness of the quantum algorithm. So the x and y, you should think of them as fixed, and this is the probability that for a given x and y, the algorithm would accept. What would happen when you take x and y to be uniformly at random, and you take them independently? What would be the expected value of this expression? So if you take x and y to be independent, then no matter what vector you got here, y is independent of that, and the expectation is actually 0. Right? So the expectation of the inner product would be 0 because each coordinate has expectation 0. Right? What would happen when you take the distribution D? Well, I claim that
X and Y are ±1 or 0, 1?
±1. Everything is ±1.
Sorry.
Right. What would happen when you take the distribution D? Right? So really I want to understand what is the expectation, of half plus hx y divided by n when x and y are sampled according to this D distribution, right? So I claim that this is similar, and this is based on this randomized rounding, to what would happen when I sample x and y to be Gaussians. And this is, you can check it by linearity of expectation. You just open this up as a sum of monomials. You can show that for each monomial this holds by the randomized rounding. Therefore, it should hold for the entire sum. The reason that I don't put equality here is that there was this small probability of abort, and this is really the only thing that could change this distribution, but this probability was very small. So up to a very, very negligible term, this is equality. Okay. And what about this thing? How does this behave? Well, when we sample x and y according to the Gaussian distribution, y was really h of x. So this is really the norm of h of x, or the norm of y. And we know that this is sigma squared times n in expectation divided by n. So this is the expectation that I get. Okay, so and sigma squared was not that small. It was like 1 over log n. So that's why I got advantage 1 over log. So already we completed the first task. We showed that there exists a okay, we didn't show the algorithm, but at least based on their statement, this algorithm of Scott and Andres gives us some advantage distinguishing between these two distributions. So what is the algorithm? It's very simple. It's similar to algorithms that Adam showed in his talk. So I'm going to first prepare a state in superposition over all the location of the strings. Okay, so I'm denoting the location of the string as the tuple, where the first bit indicates if I'm looking on the x part or the y part, and then an index to this part of this string. Okay, so I can prepare this state in superposition, and then I want to query the input. Okay, and we are in this model where we can apply this query oracle, and this just multiplies this state with xi and this state with yi. Okay, so this was the oracle model that I talked about a little bit yesterday, and it's also the same as the oracle model that Adam introduced. So just with one query to the input oracle, we get from this state to that state, and now what do? We apply the Hadamard on this part of the state. Why can we do that, actually? Why can we apply Hadamard on only the first half of the input? Yeah, so I can use the first bit to sort of control whether I apply the Hadamard or not. So you can think of it as some control bit, and I apply the Hadamard on the rest of the bits. If this is 0, and if it's 1, I'm not applying the Hadamard. So this is the third step, and finally I measure the first qubit in the plus minus 1 basis, and you can check that indeed the probability of acceptance is exactly 1/2 plus this inner product, this correlation. Okay, so this is maybe a little bit technical, but sort of the key idea here is that quantum algorithms are able to perform the Hadamard transform very efficiently. So this entire algorithm makes only one query and applies log capital N many gates. Okay, so to apply this Hadamard thing, you need only to apply log capital N many gates. So this tries to sort of exploit this fact that Hadamards are easy for quantum and sort of hard for classical. So we need to show that this is hard for a classical device, and this is our main argument. This is where most of the hard work goes into. So why is this hard for a classical device? Okay. So you asked what can I recall what is an AC0 circuit? Thank you for your patience. So this is the AC0 circuit. So we're thinking of bounded depth circuits where each gate is either an AND or an OR, and we have unbounded fanning, meaning each gate could be the AND or the OR of many of the previous gates. And we have variables or the negation at the bottom. Okay. So when I say AC0, if I don't restrict anything, that they can compute any function. So I can just compute by an OR of ends. I can compute any function. So this is sort of not interesting. So what I really care about is this model when the size is restricted and when the depth is restricted. So I want to think of the size or the number of gates as polynomial in capital N, and you should think of the input as just the bits of the oracle. So x1 up to x capital N, and the depth I want it to be constant. Okay, so these are the parameters that I'm going to think when I say AC0 in the next slide. This is what I mean. So these circuits with constant many layers and polynomial many gates. So we actually know quite a lot about these circuits. So we know that the parity function cannot be computed in this model. This beautiful line of work showed these results. And by the way, they actually define the class AC0 in this line of work. And the main result in these papers is that an oracle separation between P space and the polynomial hierarchy. So in fact, you can see that this sort of goes, this connection between the polynomial hierarchy and AC0 circuit goes way back. Okay, so by now we have many proofs for this result, that parity is not in AC0. The parity of all the bits. So I just want to check if the parity of x1 up to x capital N, is it odd or even? Okay. And if you think of the oracle, it's sort of like I want to look at the entire truth table of the oracle and say whether I have an even number of ones or an odd number of ones. And it sort of seems hard to do it with querying a few locations. Okay.
So when you say AC0, it's the same as AC0 poly and comma O1.
Yeah.
Repeat the question.
When I say AC0, I mean AC0 with poly n size and constant order 1 depth. Okay. In fact, we have some trade-offs. So we know that with constant depth, we need exponential size. So we have even stronger results than what I claim, but let's just stick with that. Okay, so this is sort of like a classical result, and we have many proofs for this result. I want to mention one of them. You can show that any AC0 circuit can be well approximated by a low-degree polynomial over the same input variables. And this is the famous result by Hastad using the switching lemma and translated to the language of polynomials by Lineal, Mansour, and Nissan. So what do I mean by that? So you take the circuit, you can write a multilinear polynomial of low degree, let's say degree polylog in capital N, such that the circuit and the polynomial have close values. So if the circuit gets a 1, the polynomial will get value, let's say 0.99. If it should get a 0 or a -1, depending on our notation, then the value of the polynomial should be close to -1. Or at least we want this to happen for most inputs. So we want this to be an approximation in L2 norm. Okay. On the other hand, you can show that the parity function cannot be approximated at all by low-degree polynomials. So if you take a polynomial of degree less than n, then the approximation is you are correct only with probability 1/2 in some sense. So you get very lousy approximation by low-degree polynomials for the parity function. Therefore, the parity function is not an AC0 circuit, right? Everything here has low-degree approximation. This doesn't. Okay, so that's sort of, okay. Of course, you need to prove that, and it takes a lot of work to prove that. So you might want to take this technique and apply it to our setting. Yeah.
The degree of the polynomial that you're talking about is the total degree?
Yes. So the question was, what do I mean by degree of the polynomial? So I think of multilinear polynomials, and I mean by degree I mean total degree. So if the polynomial is like x1, x3, x7 plus x2, x9, then the degree would be 3. Okay, so the degree of this monomial is 3. Okay. And it's without loss of generality, I can think of multilinear polynomials because I'm working over the domain plus minus 1. So I don't need to take something raised to the power 2. This would be just 1. Okay. Okay, so you can try to take this technique and apply it in our setting, but then you'll face a big obstacle. So we are trying to distinguish between the capabilities of log-time quantum algorithms and AC0 circuits. But it turns out that also log-time quantum algorithm can be well approximated by low-degree polynomials. This is a very beautiful result of Bills et al. If I had more time, then maybe I would show you that, but unfortunately I don't. Basically, you can write for a quantum algorithm that makes queries, you can write the probability of acceptance as a low-degree polynomial. The degree of the polynomial will be just the number of queries that it makes to the black box. And eventually, so this will be the degree of the amplitude, and eventually you're measuring, so then you're taking squares, so the degree will blow up by a factor of 2, perhaps. But anyway, it seems that this notion of low-degree polynomials is the wrong notion to distinguish between these two models, quantum log time and AC0, which sort of told people do not go this way, so don't try this approach. Nevertheless, we tried it, and one reason that we were optimistic that it might work is that we realized that the low-degree polynomials that arises in both cases are of very different flavor. In what sense? So when you look at the quantum log time algorithm, you can see that they sometimes would have very dense low-degree polynomials, and I will explain what I mean with more details, whereas the AC0 circuit always have very sparse low-degree approximations. So let's consider again the algorithm by Aronson and Ambanis. I claim that the polynomial that arises there is of degree 2. However, it's very dense. So let's recall what was the polynomial. It's actually written on the board still. So the polynomial was this 1/2 plus the inner product. Okay. So this was a polynomial. Oh, this was the acceptance probability of Q, right? And if you open this up, this is really a polynomial in the variables, the x variables and the y variables, right? So this is really sum over i's and over all j's going from 1 to n. Oh, sorry, n over 2. I have 1 over n outside, and I have here xi, hij, yj. Okay? So as a polynomial in the x and y variables, this is a quadratic polynomial, but you can see that it has order n squared terms. Okay. What about AC0 circuit? So in this previous work, showed that they have sparse low-degree approximation in the following sense. If you look at how many monomials participate of degree k, then this number is not too big. It grows like polylog raised to the power k. And you should compare it to the maximal number that this could get, which is something like n to the k, right? Or n choose k. So in particular, if you look at how many linear monomials of degree 1, how many quadratic monomials you have of degree 2, then this is something like polylogarithmic in n, whereas here it is order n squared. So there is a difference between these two models. Okay, so I didn't want to go into this proof, but I could say that it is based on these classical results of Hastad. So it is based on the switching lemma and all these results. Yeah. Right. And in fact, it's sort of so to go from this. So from the switching lemma, you get that you have very good low degree approximation, and from the fact that an AC0 circuit is a Boolean function, you get that this is sparse. So the fact that it's Boolean plays sort of important role here. However, the acceptance probability of a quantum algorithm is not a Boolean function, if you think about it, right? So here we can have values that are very close to 1/2 for many inputs, which is one reason why it doesn't work for the quantum algorithms.
What was the original motivation here, by the way?
The same motivation. Yeah, we just sort of were stuck. So intuitively, the fact that this is dense and this is sparse explains why this can somehow notice that the distribution D is not random, whereas here we do not notice. And I want to explain that. So what happens when we try to evaluate this polynomial over this distribution D, right? When we take the expectation of this. So we already talked about it earlier, but okay, so when we take expectation over D, okay. You can see, or in fact, you can take this even outside. You can see that xi and yj, right, they have a very small correlation. We said that the correlation is actually roughly hij, so roughly 1 over square root n. So the only reason that we're able to have that this sum is big is because we have many terms. Okay? If we had like 7 terms, that we would accumulate only 7 times 1 over square root n. So this is sort of intuitively why we have to be dense to notice the difference between D and U. Unfortunately, it's not that simple because maybe an AC0 circuit have also higher degree terms, not only quadratic terms. So we sort of need to handle all degrees simultaneously. Okay, so I want to take this intuition and I want to make it into a proof. So that's sort of the remaining part of the talk. How much time do I have? When do I need to finish roughly?
12.
Around 12. Okay, so to be more precise, instead of talking about sparsity, I want to talk about the sum of the coefficients, the sum of the absolute values of the coefficients. Okay, so here I'm like looking at all coefficients here of these monomials. So here I have that each one of them is 1 over square root n times 1 over n, and I have n square of them. So the sum of absolute values of the coefficient is rather large here. And what I can show about AC0 circuit is that if you take the sum of absolute values of the coefficient in an AC0 circuit, this is not too large. This is something like polylog raised to the power k. Okay, if you are not familiar with this notation, I will just show it in the next slide. So this is just the coefficient of the monomial product xi where I is in S. Okay, so I want to now try to take this sparsity of AC0 and try to apply it and to get that indeed the distribution is pseudo-random, but this would be the first attempt, namely it would fail, right? So there would be something going wrong here. So a very useful and well-known fact about Boolean functions is that you can uniquely write them as a multilinear polynomial. Okay, this is called the Fourier representation of a function. There were some exercises in the problem sheets that you needed to prove that they exist and that they are unique. Okay. So you can just write the f of x as the sum over all possible subset of the number between 1 to n. The coefficient for each subset, this is just a real number, times the monomial for the relevant monomial, the product of xi where I is in the set S. And I'm thinking of the Boolean domain as plus minus 1, where minus 1 represent true and 1 represent false. So let's see an example. The end of 2 variables. I claim that it can be written as this polynomial. So how, okay, I claim it, why is it correct? So we can just check. We can just check on all 4 possible inputs and see that indeed the polynomial and the function agrees. Okay, so I made this check here, and you can verify it for yourself. The nice thing about this multilinear polynomial is that it naturally extends a Boolean function, which is a discrete object, into a continuous object, right? So this is now an object over R to the n. So I can, for example, look at this discrete function, and now I can ask, what's the value of this polynomial on 0.3 and 0.7? And I get some answer back. And this answer is actually meaningful. Okay, why is it meaningful? It allows me to go between the discrete setting and the Gaussian setting. So if f is a multilinear polynomial, I can show that the expectation under this randomized rounding is the same as the expectation under the Gaussian distribution. Okay? And again, there is some kind of, this is not equality because I have this probability of abort, but that's the only thing that could go wrong. And similarly, the expectation under the uniform distribution is the same as the value of the multilinear extension on the all zeros vector. Okay, so this is also in the problem set. Okay, so now recall what we wanted. We want to show that the expectation under the distribution D is similar to the expectation under the uniform distribution. But now, since this is very similar to that and this equals that, we just need to show that these two are very close by. So that's what we want to show. We want to show that for any AC0 circuit, the expectation under this Gaussian distribution is similar to the value of the function on the all zeros vector. Okay. So let's try to do it in a straightforward fashion. So let's just write this polynomial, the sum of all monomials, and let's just try to bound it term by term. Okay, so I just use linearity of expectation to say that the expectation of f on z, where z is drawn according to g, is simply the sum over all coefficients times the expectation of the monomial. And what does f of 0 gives me? It just gives me the empty term. Okay, the empty coefficient, which cancels out with this one. So all I'm left with is all the non-empty sets. Okay, so this so far is just equality. And now I'm going to recall that I took Gaussians whose mean is 0. Right? So G was this Gaussian distribution whose mean was 0. In particular, the expectation of Z1 was 0. The expectation of Z7 was 0. And also the expectation of odd moments, like Z1 times Z3 times Z5 is 0. So we can sort of just forget about all the odd moments and just consider all the monomials here of even degree. Okay, so now I'm rearranging stuff. I'm summing over all possible degrees, or all possible L between 1 and n over 2. I'm taking all possible coefficients of size 2 times L, and I'm asking what's the contribution of these guys. Okay, so far it's just equality. I didn't do much. What about the even terms? Recall that this is a Gaussian distribution, and we know something about, the Gaussian distribution is defined by the means and the covariance matrix. So in fact, we can sort of calculate all the moments just by the covariance matrix. And the covariance matrix is fairly simple. It has this nice structure. Sorry. So the covariance matrix has a nice structure. It is identity, then Hadamard, and identity. In particular, all the entries here, all the non-diagonal entries are very small. Okay. So you can calculate and see that the degree 2L moment is roughly L over square root 10 to the L, based on Isirleth's formula, which I will not go into, but this is a well-known formula on Gaussians. Yeah, let me finish this and then let me take some questions. And what do we do next? Well, now we bounded this, by this term, but now we have the sum of absolute values of these coefficients, and we already got this a bound on the sum of absolute values of coefficients of degree L, so we can replace it with polylog to the power 2L, and this is more or less what we got. And notice that this is pretty good when L is small. So when L is 1, this is roughly polylog times 1 times square root 10, which is what we expected it to be, what we sort of set up to prove. When L equals 2, it's even smaller, but when L gets bigger, let's say square root n, then we don't have nothing meaningful here because L over square root n is bigger than 1, and this entire thing is bigger than 1. So the contribution of the first term is what we wanted, but we don't know how to bound the large terms. Okay, yeah.
So just wondering even just for the first step of eliminating the odd ones, the ZIs are not independent. So don't you, if they were independent, then I can see why sort of an odd thing will just give you a 0, but...
So there are still a multivariate Gaussian distribution, and still every
it's a product of these, you think?
Yeah, so it's still true that a multivariate Gaussian distribution, even with covariances, if the means are zeros, all the odd moments are 0. And you can see it just by the fact that, everything, you can just multiply everything by -1, and this would be
symmetric,
right? So this would cancel out. But you can also just use this series of theorems that just tells you that the odd moments are 0. Okay, so that's, I mean, but it's, and then to go from here to here, I use this bound. It's the sum of absolute so the question was, how did I bound the Fourier coefficient? And I'm using the fact that I know that F is an AC0 circuit, therefore the sum of absolute values is not too big. It's something like polylog raised to the power 2L. Okay. So this sort of failed. We were stuck on this for a long time. You can change many things, but what you need to really change is how you think of the problem. So you need to do some kind of thought experiment. So I want to rethink of this Gaussian distribution. So instead of sampling a Gaussian vector at once, you can think of it as a result of a random walk making a lot of tiny steps. So let's see why this holds. So let's say that you sample Z1 up to Zt according to this distribution G. And you sum them up and divide by square root t. You take these Z1 up to Zt, you take them independently of one another. When you take the sum of independent Gaussians, you get a Gaussian. The mean would be the sum of the means, and the variance would be the sum of the variances. So really, you got the same distribution, but you sort of wrote it in a different way. And if you take the limit of t going to infinity, this is really sort of expressing a Gaussian as a result of a Brownian motion that eventually, you stop it at a certain time, and then the point that you sampled is really distributed according to a Gaussian distribution. So how does this help us? The fact that we represented, the Gaussian as a sum of small vectors. We can now try we want to show that the expectation value of the function at the origin is similar to the expectation at the end. But we can think of this as a step that takes t small steps, and just show that for each small step, I'm not changing the value of the function by much. Okay? So this is really a hybrid argument. I'm going to consider t plus 1 hybrid. The first one is just the all zeros vector. And the ith one is the sum of the first I random variable divided by square root t. So when I go from the I to the I plus 1, I'm adding zi plus 1 divided by square root t. So I'm adding a small vector. And the ht is really distributed according to the Gaussian distribution. So really, I want to understand what happens when I'm making these t steps. Okay, so this was a thought experiment. So you can just pick t as you wish. You can take it to infinity, and this would give a Brownian motion. We sort of analyze it using elementary tools and not applying stochastic calculus. So we just took t to be a very large number. Let's say n to the 100. And the claim is that the difference between two consecutive hybrids is very small. The expectation of f on the I plus 1 hybrid is similar to the expectation of the ith hybrid, and the difference is at most polylog divided by t times square root n. Now, why would this claim be enough for the final statement? We can just apply triangle inequality, right? If we know that the difference between each two of them is small, then we know that the difference between the first one and the last one is not too big. How big? The sum of these guys. So each one contributes polylog divided by t times square root n. I have t of them, so overall I will show that the difference is at most polylog divided by square root n. Okay. So finally, we want to show this, the claim, that we don't accumulate much by each small step. So the first step, surprisingly, would be exactly like the failed attempt, but now this would work. Okay? And the fact that it would work is the fact that we shrunk the vector. And the fact that we shrunk the vector sort of kills off all the high degree terms. Okay, so we'll see this in a bit. And the general case, and this is sort of more mysterious, is that the ith step is similar to the first step. And this is using something on the class of AC0 functions. And here we need to use the fact that if I take a circuit and I can fix some of its input variables to constants, then I still get a circuit, which is of size at most s and depth at most t. So this family of functions is sort of closed under fixing some of the variables. So really this beautiful lemma sort of translates the difference between two close by vectors to the difference of 0 and a small vector. Okay, so I want to show you the first step. It's very similar to what we've seen before, but now I'm analyzing, h1 minus h0. h0 is really 0. h1 is distributed according to the Gaussian distribution, but I'm dividing everything by square root t. And think of t as huge. It's a really huge number. So what would happen? Exactly the same as before. We analyze it term by term. But each zi is multiplied by 1 over square root t. Okay, so degree 2L terms are divided by t to the L. And then let's see what happens. So when L equals 1, so these are the quadratic terms, we get something like polylog divided by t times square root n. So this is roughly what we also got earlier. What happens for higher degree, for degree 4 or 6? Well, we are dividing now by t squared or t cubed, and we thought of t as really huge, so we can really take t to be as large as we want. So this is sort of negligible. Everything above the quadratic terms is negligible in this calculation. This was very surprising to us, but then you ask people that are doing stochastic calculus, and they know it. So when you analyze Gaussian, only the second derivatives matter, which means that only the quadratic approximation locally matters. So that's sort of what happens here.
So t is polynomial in capital N or in small n?
In capital N. But you can think of it as exponent. I mean, it's just a thought experiment. So
it needs to kill capital N in the
right,
because you have L over T.
Yeah. So we picked it to be polynomial in capital N. Yeah. Okay. I will not go over the reduction from the general case to the base case, but I would rather recap and maybe mention an open question. Okay. So to recap these two talks, our main result was an oracle separation that shows that BQP can go beyond the entire polynomial hierarchy relative to an oracle. And Scott Aronson reduced the problem to the following game. You get two black boxes, one according to the uniform distribution, another according to the distribution D, and you need to tell which box you got. He showed that the super fast quantum algorithm can tell the difference, and today we showed why AC0 circuits, which is the analog of the polynomial hierarchy, cannot tell the difference. And the main difference we use between classical devices and quantum algorithms is this notion of dense versus sparse polynomials. Okay, so in particular, if you want to prove for another model that this distribution is pseudo-random, you want to prove lower bounds for decision trees, you just need to prove that they are sparse, that the polynomials that represent them are sparse, and you only need to prove it on the second level. And you can actually prove it, and building on this, you can get more results of this flavor. Okay, so I want to mention one open problem. This will be very provocative. It's sort of related to Thomas' talk. I want to ask, what about interactive proofs? Can an all-powerful prover convince you that two strings are correlated? So think of capital N as really exponential. So you have two exponentially long strings. If the prover was a quantum device, he could tell whether or not they are correlated. But can he convince you a classical verifier that they are correlated? Well, our results rules off an interactive proof with constant many rounds. And this is denoted by AM or Arthur Merling. And why is that? So we showed that correlation is outside the polynomial hierarchy, but in fact, Arthur Merling is inside the polynomial hierarchy. So everything that you can prove with constant many rounds is inside the polynomial hierarchy. What about if you don't limit the number of rounds to be constant and you allow them to be polynomial? And this is really IP. Can you prove it? Okay, why is it I see a lot of worried faces. So we know that IP equals P space, but this proof doesn't relativize. And the question is this a separation of BQP and IP with respect to an oracle? And I mean, I don't see any algorithm to any protocol that proves that two strings are correlated. and it might be the case. But so this is still an open problem, and I would be very happy to talk about it. In the breaks.
The problem is that P-space would be enough for this, right?
No, it is in P-space, but IP doesn't equal P-space relative to an oracle.
But this is not a relativized question. You're asking about you're getting the string.
No, so
I see you're getting an orchid. Okay.
so I think of this query model, where is it? Okay. So I have an IP conversation, but I also have access to these two strings via oracle access. Okay. Okay. So, yeah. Thank you very much.
Okay, so we're short on time, so.
I think it will take 3 minutes to hook up.
Okay, so any short questions? Any?
Maybe a 3-minute break.
While the read hooks up.